Hey there and welcome. So, have you ever found yourself just staring at a list of statistical tests feeling completely and totally overwhelmed? If that's you, you're in exactly the right place. Today, we're going to demystify that whole process. We'll give you a clear roadmap so you can choose the right test every single time. Think of this as getting the big picture before you even have to crack open the textbook.
Okay, so here's how we're going to get you from confused to confident. First, we'll talk about that statistical test maze you're probably stuck in. Then we'll uncover your data's secret identity by understanding something called its level of measurement. We'll break down the three main levels, I'll show you a super simple trick to tell them apart, and then, the main event, we'll use all that new knowledge to actually choose the right test. We'll wrap things up by looking at where this all leads, which is the very first step toward understanding causality.
All right, let's be real. Every single person who's studied statistics has been right here. You've got your data, you've got your research question, but you're facing what just feels like this impossible labyrinth of choices. I mean, it's this exact question that can bring a research project to a grinding halt, right? T-test, ANOVA, chi-square, they all sound so complicated, so abstract, and it is not obvious which path you're supposed to take. But what if I told you there's a simple key that unlocks this entire puzzle? That's right, it turns out you don't need to memorize 100 different rules. All you really need to do is understand the nature of your own data. The answer? Well, it's been right there with you the whole time. So the secret weapon for all of this, the key to the whole thing, is a concept called the level of measurement. I know, it sounds a little formal, but trust me, this is the one foundational idea that once you get it, makes everything else just click into place. You know, put simply, the level of measurement is just a way to describe the properties of your data. A good way to think about it is like your data's personality type. And just like with people, once you understand its personality, you know exactly how to interact with it. And this right here, this is exactly why we're focusing on this. This is not just some abstract theory, it is the single most practical tool you have. If you can identify the level of measurement for your key variables, your independent and your dependent variables, you are literally 90% of the way to choosing the correct statistical test. It's really that powerful. So what are these levels? Well, there are really three main characters we need to get to know. We've got nominal, ordinal, and interval ratio. Let's break them down, one by one. First up, we have nominal data. The easiest way to remember this is to think of names or categories. You're basically just putting things into different boxes. For example, male or female, or different religious affiliations. The key here is there's no logical order or ranking. One category isn't higher or better than another one. They're just different. Next up, we have ordinal data. Now this is a step up from nominal. Like nominal data, it has categories, but this time the categories have a logical order. Think about something like educational degrees. A master's degree is definitely higher than a bachelor's. But here's the crucial difference. The gap between the steps isn't necessarily equal. We know a master's is more than a bachelor's, but is that jump the same as the jump from a high school diploma to a bachelor's? Probably not. We can't assume the spaces between are equal, and that is what makes it ordinal. And finally, we have the top level, interval ratio data. This is the one that has it all. It has categories, it has a meaningful order, and this is the most important part. The distance between each value is equal and fixed. The difference between being 25 and 26 years old is exactly the same as the difference between being 50 and 51. It's 1 year. This is what we typically think of as numerical data. And this table here just lays it all out perfectly. You can really see the progression. Everything has categories, nominal stops there, ordinal adds an order, and interval ratio adds that final critical piece, equal spacing. Seriously, this table is a great little cheat sheet to keep handy. Okay, so the theory is great and all, but how do you actually apply this when you're staring at a spreadsheet full of numbers? Let's go over a really simple but incredibly effective trick to tell true numerical data apart from the others. So this is a super common trip-up. You open your data file in SPSS or whatever software you're using, and you just see a column of numbers. For a variable like sex, you might see a bunch of ones and twos. It's so tempting to think, oh, that's numerical. But those numbers are often just labels. A 1 might stand for male and a 2 for female, but you could have just as easily used 99 and 150. The numbers themselves don't mean anything. They're totally arbitrary. So here's the trick. Just ask yourself one simple question. Does taking the average or the mean make any sense? So look at the example on the left. If you calculate the average age of your group and get 25.3, Well, that's a meaningful number, right? Now look at the right. If you take the average of your sex variable and you get 1.6, what on earth does that mean? It's complete nonsense. So here's the rule. If the average is meaningful, your data is interval ratio. If it's meaningless, it's either nominal or ordinal.
All right, this is the moment we've been building up to. We understand levels of measurement, we have our little shortcut. Now, let's put it all together and see how this leads us step by step directly to the right statistical test.
The whole process is basically a simple flowchart. First, you always start with your dependent variable. That's the outcome you're trying to explain. Then you ask our cheat question. Is it numerical? Does taking an average make sense? Once you've answered that, you just have to look at your independent variable. That's the thing you think is causing the change. And just like that, the right test will basically reveal itself.
So let's follow that first path. Let's say your dependent variable is numerical, something like income. Okay, now you look at your independent variable. Is it a non-numerical variable with just two categories, like comparing men and women? Boom, you use a t-test. What if it's a non-numerical variable with more than two groups, like comparing income across people with a high school, bachelor's, and master's degree? Well, that's an ANOVA. And what if your independent variable is also numerical, like you want to see if years of education is related to income? Now you're looking for a correlation, and that's Pearson's R. See how logical that is? Now, what about that other path? What if your dependent variable is not numerical? Maybe you're trying to predict something like voting preference. Democrat, Republican, Independent. That's a nominal variable. If your independent variable is also not numerical, like gender or race, then the test you're looking for is a chi-square. It's designed for one specific job, to look for relationships between categorical variables. So what you've just learned is how to do what we call bivariate statistics, which is just a fancy way of saying you're testing the relationship between two variables. But it's really important to understand where this fits into the bigger picture of doing science. This is the first, absolutely essential step on a much longer journey.
Let's just put this into context for a second. Univariate stats, that's when you're just describing one variable at a time. The tests we just covered, the t-test, ANOVA, chi-square, those are all bivariable. They test if a relationship exists between two variables. The next level up from there is multivariate, where you test that same relationship, but you do it while also accounting for the influence of other variables.
And this is the absolute key takeaway. A t-test or a chi-square test can tell you that two things are related, but it can't, all by itself, tell you that one thing causes the other. Finding a statistical relationship is just step one. Proving causation, now that's the ultimate goal, and it's going to require a lot more evidence. So what does that evidence look like? Well, as you move forward in your stats journey, you're going to learn about these key criteria for causality. And here's the cool thing. You've already mastered the first one today, which is finding a statistical relationship. But you'll also learn how to prove the cause came before the effect, how to rule out fake relationships, and how to make sure there isn't some other better explanation out there. So, we're going to leave you with this thought. By learning how to choose the right test, you've mastered the first and most fundamental step in all of science, finding out if two things are related. The really exciting question that comes next is, what does that relationship actually mean? And how can you be absolutely sure it's real and not just a coincidence? That's the challenge that lies ahead. We hope this has helped clear the path for you. Thanks for joining us.